Alright, last video for divergence, and it's a biggie, okay, because we talk about the divergence theorem, okay? And so what this is saying is that we have a region D to which Green's theorem applies. So again, you might have to remember that there's orientation, like make sure to look up those conditions. And we have N as the outward unit normal vector to our region D, and we have a vector field that's we're looking in R2 because that was the conditions for Green's theorem. Okay, then at least in this case, we started in the last video. We introduced the ideas of this line integral over the boundary with the dot product of the vector field and the unit normal vector, and then the double integral of the divergence over the region. And these actually end up being equal, okay? So this is really, really interesting and really important. Okay, so the line integral over the boundary, where we're integrating the dot product of the vector field and the unit normal vectors, same as the double integral of the divergence, okay? And in particular, when we're looking at that total net flow over or across the boundary, that we think of as the flux. Okay, so and actually this idea of flux comes up in electrical fields all the time and magnetism. Okay, so whenever you take physics and all that stuff, know that this is actually how they're computing flux. Okay, so great. And then so here, really just to summarize what we talked about in the divergence theorem, total flow across the boundary, we're saying is the same as the total net flow over the region. Okay, so we can look at either one and get the same thing. Okay, so rather than computing flux, we could do double integral of the divergence. Maybe. Okay, alright, so foreshadowing. Find the flux of this over the unit circle centered at the origin in two different ways. Okay, so again, flux, we want to compute, at least according to the definition, the integral over the boundary of D, and then f dot n ds, okay? And so, well, one way is to compute directly. Okay, and we could do this. It isn't too challenging, right? You just have to do it properly. But instead, I maybe want to use the divergence theorem. Okay, and so we know here that we have D is the unit disk centered at origin. Okay, and so what we should be able to say here is that if we look at, and so does Green's theorem apply? And so again, can we orient it so that we're always on the left and like, yeah, this is going to be okay. So again, maybe just have those hypotheses for Green's theorem handy, but I mean, that's fine. So our assumptions are met, okay, and so all we have to do is the double integral over D of the divergence dA, and if we actually compute this, I think when you look at the vector field, you do the partials, well, you get 0. Oops. And so we're just going to say that the flux here is 0. Okay, and you would confirm that the other way using direct computation. Okay, so two different ways, very handy to compute flux. All right, and so this is then the videos for this week. We talked about divergence, algebraic definition, pretty straightforward, just partials add it up, okay? And then with geometry, we're thinking flow out minus flow in for infinitesimal net flow, okay? And then we introduced the idea of flux and incompressible as well, just to throw in a few vocab terms, okay? All right, so that concludes this. We'll see you in class this week.